Team 1009. I am Anant Narayanan.
I am Siddhi Agarwal.
And I am Rishabh Banerjee.
Our coach is Dr. Neelesh Kumar from Sri Venkateswara College, University of Delhi.
This is our solution to problem A of SCUDEM 6 2021, hair pulling to line your nest.
Now, coming on to the introduction, avian species such as genus Pareidae exhibit a puzzling practice of kleptotrichia where they snatch hair from live mammals to incorporate into their nest, as it provides insulation and may deter parasites. In this presentation, we study its impact on the bird population. We introduce some key terms that are important for understanding the essence of the model. We will focus on the bird species genus Pareidae that include tits, chickadees, and titmice. They are found in the Palearctic regions, tropical forest, as well as the boreal forest, which include Eurasia, Europe, Africa, and North America. The insulation property of mammal hair forms a big aspect of our model. These are the assumptions of our model. The bird population grows logistically. The growth rate of the population is an increasing function of the quality coefficient or the quality and extent of mammal hair used in creating the nest. The proportion of population engaging in kleptotrichia per unit time is assumed to be constant. The per capita death rate of young lynx is inversely proportional to the quality coefficient. The only method of obtaining mammal hair for nest is kleptotrichia. There is no migration of birds in the area under consideration. The proportion of young lynx in the population is constant at any time t. The primary benefit of kleptotrichia is the insulating value of the mammal hair.
Main notations. The main notations are as follows. The symbol xt is the population of birds at any time t. The symbol yt is the population of young lynx at any time t. K is the carrying capacity of the population. Q is the quality coefficient. RQ is the growth rate of population as a function of quality coefficient. M, which belongs to the interval 0 to 1, is the proportion of young lynx in the population at any time t. Alpha is the per capita death rate of adult birds due to kleptotrichia. L is the per capita death rate of young lynx due to quality of nesting material. Now please note, other notations have been introduced while explaining the model. Model overview. We have divided our model into two parts. First, hot urban areas, that is tropical forests, and second, Palearctic regions, that is boreal forests. For each region, we have selected three mammals that are most likely to be the victims of kleptotrichia based on the data provided to us. Keeping in mind the assumptions of our model, the general properties of hair of each mammal, their attacking tendencies, and local climate conditions have been considered while calculating the coefficients used in the formation of our differential equation model. Word equation. We formulate the following word equation. Rate of change of population of birds is equal to logistic growth of bird population minus death rate of young lynx due to the quality of nesting material minus death rate of adult birds due to kleptotrichia.
Using the word equations and keeping in mind the assumptions of our model, we formulate the following differential equation. D by dt of xt is equal to r of q times 1 minus x by k times x minus ly minus alpha times x minus y. That is, d by dt of xt is equal to r of q times 1 minus x by k times x minus mlx minus alpha times x minus mx. The above equation can be simplified to obtain the following. D by dt of xt is equal to r of q times 1 minus x by k times x plus m minus 1 alpha minus ml times x. The model parameters. For each submodel, consider the three mammals selected to be M1, M2 and M3. For each mammal Mi, we define beta I to be the attacking tendency of Mi during kleptotrichia, theta I to be the insulation coefficient of the hair of Mi, gamma I to be the anti-predation coefficient of the hair of Mi, and delta I to be the miscellaneous coefficient of the hair of Mi. All these coefficients lie in the interval 0, 1, which is open at 0 and closed at 1. We now define some important coefficients used in the model. We begin with the climate coefficient. It is denoted by C and belongs in the interval 0, 1, which is closed at 1, open at 0, and is the measure of usefulness of the insulation property of mammal hair for a given local climate condition. Now the extension coefficient. The extension coefficient denoted by E, which again belongs in the interval 0, 1 closed at 1 open at 0, is the proportion of the bird population engaging in kleptotrichia per unit time. The quality coefficient. Now for each mammal Mi, we define the quality index of the mammal hair to be Qi, which is equal to theta I times gamma I times delta I, which we defined previously. The quality coefficient denoted by Q again belongs in the interval 0, 1 closed at 1 open at 0 and is given by Q is equal to C times Q1 plus Q2 plus Q3. The population growth rate. The population growth rate, as mentioned in the assumptions, is an increasing function of the quality coefficient. We define the function r of q from 0, 1 to r as r of q is equal to r0 plus eq upon 1 plus q. Here, r0 is the base growth rate when no individual of the bird population engages in kleptotrichia. The coefficient of attack. The coefficient of attack denoted by beta is the probability of an individual bird to be attacked during kleptotrichia. It is given by beta is equal to beta 1 plus beta 2 plus beta 3 by 3. That is the average of the attacking tendencies of the 3 mammals selected. The per capita death rate of younglings due to the quality of nesting material. It is denoted by L and is inversely proportional to the quality coefficient Q and is given by L is equal to E by Q. The per capita death rate of adult birds due to kleptotrichia. It is denoted by alpha and is given by alpha is equal to beta times E. Note that in the process of solving the model, the values of the parameters have been calculated as per the data provided by SCUDEM along with our own online research.
Hot urban areas and tropical forests. The 3 mammals most likely to be victims of kleptotrichia in these climatic conditions are humans, koala, and klipspringer. They are taken as M1, M2, and M3 respectively. According to the data provided to us, the mammals in these regions have a very small tendency to attack birds during kleptotrichia. Since thermal benefits are not so advantageous in these regions, the climate coefficient is assumed to be really small. Human hair has useful anti-predatory properties but are not good insulators and are a threat to younglings as they are thin and strong and cut off their circulation. Koala hair and klipspringer hair are excellent insulators and conserve moisture as well, but do not possess anti-predatory properties. These mammals are generally harmless and do not tend to attack the birds that pluck their hair. Considering this information, we set the value of the coefficients. We set the initial bird population to be 20, carrying capacity of the population to be 150, and proportion of younglings in the population to be 0.3. The base growth rate is assumed to be 3. We solved the model by varying the extensive coefficient to understand the effect of kleptotrichia on the bird population. Case 1. E is equal to 0.1. Corresponding to this value, we solve the differential equation numerically and plot it to observe that the bird population grows logistically and achieves a stable state at a population level of approximately 125 birds. Case 2. E is equal to 0.4. Corresponding to this value, we again solve the differential equation numerically and plot it to observe that the bird population grows logistically and achieves a stable state at a population level of approximately 70 birds, this time lower than our previous case of E is equal to 0.1. Case 3. E is equal to 0.65. Corresponding to this value, we finally solve the differential equation for the third time and plot it to observe that the bird population declines logistically and achieves a stable state at a population level of approximately 12 birds, which is way low than our previous cases.
Now, we move on to the Palearctic regions and the boreal forests. The 3 mammals most likely to be the victims of kleptotrichia in these climatic conditions are Virginia possum, red squirrel, and domestic cow. They are taken to be M1, M2, and M3 respectively. According to the data provided to us, the mammals in these regions have a greater tendency to attack birds during kleptotrichia. This is due to the relatively larger size of the mammals in these regions as compared to the tropics. Since thermal benefits are so advantageous in these regions, the climate coefficient is assumed to be large. Mammal hair in these regions is highly useful because of its high insulation coefficient. Opossum, squirrel, and cow hair have excellent insulation properties but are not so useful as anti-predatory materials. These mammals have a greater tendency to attack. For example, the red squirrel is known to eat bird eggs and attack small birds. Considering this information, we set the values of our coefficients. We also set the initial bird population to be 20, the carrying capacity of the population to be 150, and the proportion of younglings in the population to be 0.3. The base growth rate is assumed to be 3, and we solve the model by varying the extension coefficient to understand the effect of kleptotrichia on the bird population. Case 1. E is equal to 0.4. Corresponding to this value, we solve our differential equation numerically and plot it to observe that the bird population increases logistically and achieves a stable state at a population level of approximately 80 birds. Case 2. E is equal to 0.8. Corresponding to this value, we again solve our differential equation and plot it to observe that the bird population increases logistically and achieves a stable state at a population level of approximately 40 birds, which is less as compared to the previous case, where E is equal to 0.4.
Now, coming on to the conclusion of hot urban areas and tropical forest, the thermal benefits of mammal hair are not so useful in these regions due to high temperatures, while mammal hair does tend to protect the younglings from predators such as snakes, largely due to the smell of large mammals. The risk of kleptotrichia outweigh the benefits. This can also be inferred from the solution of our model. The population grows logistically when a small proportion of the adult population is engaging in kleptotrichia. As the extent of kleptotrichia increases, the stable value of the population level tends to decrease. For E equal to 0.62, it can be observed that the population declines. The risk completely outweigh the benefit for large value of E. This also explains the fact that the kleptotrichia is not so commonly observed in these regions. Conclusion of Palearctic region and boreal forest. The main reason for kleptotrichia in these regions is the high insulation coefficient of mammal hair, which protects the younglings by keeping them warm in the cold temperatures. However, due to their large sizes and biologically observed behavior, these mammals also have a greater tendency to attack the birds. As the extent of kleptotrichia increases, the stable value of the population level tends to decrease. However, to the relatively hotter regions, even for E equal to 0.8, it can be observed that the population grows logistically. The benefits outweigh the risk as the insulation property exponentially increases the chances of survival of the younglings, which further contributes to a higher growth rate of the population. This is a reason why kleptotrichia is commonly observed in the climate. While the model explains the general impact of kleptotrichia on the population of birds, it does come with its limitations as well. There are many methods of obtaining mammal hair, for example, hair shed in vegetation, etc. This model focuses only on kleptotrichia and its impact. Migration of birds is common in the cold regions, which has not been accounted for in this model. The proportion of younglings in the population may vary with time. There are many factors other than the quality of nest material which may affect the survival of the younglings. There might be other benefits of mammal hair and hence kleptotrichia which have not been studied yet.
We are really grateful to all the researchers around the world as the information gathered online played a huge role in the formulation of this model. Finally, we would like to thank the SIMIODE authorities for providing us with this opportunity. Happy modeling!